the last lecture on Frobenius-Fuch's method, that is in the fourth lecture, we have applied the power series method to few simple problems, and we have promised that we shall apply the power series method for the solution of Legendre and Hermite differential equation. Now we come to the Frobenius-Fuch's method proper. As per the first theorem, if the point of expansion be a removable singular point, then the solution can be written as y of x. Then the solution can be written as y of x is equal to summation over k is equal to 0 to infinity ck x minus a to the power m plus k, with c0 is not equal to 0. This extra exponent or index that has been introduced by the Frobenius-Fuch's method is determined by the initial equation. That is, if we differentiate it once and twice and plug this in the original differential equation, then we'll end up with an identity, and by equating the lowest power of x to the x minus a in this identity, we get the initial equation, which enables us to determine the index m. And this second theorem is related to this. That is, before we go into the proper, we first write that let the equation be in the form y double prime y double prime plus q1 y prime plus q2 y is equal to 0. Then we applied all these things over here, and the resulting equation that we will get is summation over k. If we differentiate it twice, it is first term is m plus k, second term is m plus k minus 1 x minus a to the power m plus k minus 2 from this term, plus q1 of x summation over k is equal to 0 to infinity m plus k x minus a to the power x minus a to the power m plus k minus 1 plus q2 of x summation over k is equal to 0 to infinity ck x minus a m plus k is equal to 0. If q1 and q2 may also be expressed in this way, as we have shown in the other class, that there will be another sum beta sum and there will be a gamma sum, and finally if we correlate the lowest power means if we put k is equal to 0, the lowest power is x minus a to the power m minus 2. The lowest power is lowest power of x minus a is m minus 2. This gives you an initial equation. There is another initial equation by collecting the coefficient of next higher power. So we shall get the roots of initial equation, which we shall come right now from the discussion. And the second theorem, the theorem is that the Theorem-II says, before that, let m1 and m2 be the roots of initial equation. Theorem-II states, if m1 difference m2 is not an integer, then two roots can be obtained as y is equal to a1, y with m1, m is equal to m1 plus a2, y with m is equal to m2. As for example, say the roots are 0 and half. So the roots are distinct and they do not differ by an integer. So we can get two roots. The second, this B part says, if m1 is equal to m2, only one root can be obtained. Root can be obtained by Frobenius-Fuch method. The other root can be obtained easily, so the general solution can be written as a1 y at say the m1 m2 is, and then a2 del y del y del m with m is equal to m1. But note that this is not the Frobenius-Fuch method. It is an outcome of some other methods called the Wronskian's technique. And thirdly, if m1 difference m2 is an integer, what happens? The larger root definitely gives a solution. The smaller one may or may not yield a solution. This is the statement of second theorem of Frobenius-Fuch method. We shall first take few examples of the differential equation for which the theorem can be applied. Firstly, we consider this example on Theorem-I, where the roots do not differ by an integer. First example on Theorem 1a. So we consider an example like this. The differential equation 4xy prime y double prime plus twice y prime plus y is equal to 0. Note that x is equal to 0 is a singular point. X is equal to 0 is a singular point. So we need to, and furthermore, so P0 is 4x, P1 is 2, P2 is equal to 1. In terms of Q, Q1 is 1 upon 2x and Q2 is 1 upon 4x. So if we go to x function, about x1 is x times q1 is equal to half, and x2 is equal to x squared times q2. This is equal to x by 4. At x is equal to 0, this is half and this is 0. So they are finite. So the x is equal to 0 is a removable singular point. X is equal to 0 is a removable singular point. So we assume the solution to be and our aim is to find out m. So we will write this. We plug this in into this differential equation. 4x summation over k ranging from 0 to n ck m plus k from first derivative m plus k minus 1 from second derivative m plus k minus 2. Then 2 ck m plus k x to the power m plus k minus 1, and then we collect the coefficients. You see that this power is x to the power m plus k minus 1. This term has the similar power. So we take 2 summation over ck. M plus k is common, so m plus k is taken common. Then this term is 2 times m plus k minus 1 plus 1. On simplification, this gives k is equal to 0 to infinity is has to be written everywhere. This is 2m plus 2k minus 1. This is 2m plus 2k minus 1 x to the power m plus k minus 1. This being an identity, the coefficient of every power of x should be same on the left hand side as on the right hand side. The lowest power of x to the power m, if we put k is equal to 0, this is m minus 1. So coefficient of that is x to the power m minus 1 is, you see, as when k is 0, this is x to the power m minus 1. If we put k is equal to 0, the term is twice c0 m into, here we have 2m minus 1, and this term contributes nothing to this because k starts from 0. So for k is equal to 0, it is x to the power m, x to the power m plus 1 onwards. So this is equal to 0. This equal to sign may create confusion, and which gives you m is equal to 0 or half, as c0 is not equal to 0. So we see that there are two roots, m1 and m2. m1 is 0 and m2 is half. So m1 is 0 and m2 is half, and they differ via non-integer. So the Frobenius-Fuch method says that the second theorem says that it is possible to get both the solution, one by putting m is equal to 1, m is equal to 0, other by putting m is equal to half. We shall take up this example later on. Then we consider another example to show that the roots of the initial equation do not differ by an integer. The second example is x square y double prime plus xy prime plus x square minus y square is this. This is actually Bessel differential equation, although we have already considered Legendre differential equation without uttering the name. Now we see that Q1 is 1 by x and Q2 is x square minus alpha square by x square. So if we so x1 is x and x2 is x square minus alpha square. So both of them are finite at x is equal to 0. So x is equal to 0 is a removable singular point. So we can apply the theorem. The solution is y of x is equal to summation over k is equal to ck x to the power m plus k with c0 not equal to 0. If we apply this here, we get ck m plus k minus 1 x to the power m plus k minus 2, but this one will raise the power by 2, so it is again x to the power m plus k. And for the second term we will have summation over ck m plus k, again the power is raised to x to the power m plus k. And for other two term we will have plus x square minus alpha square. Alpha is any real finite quantity, ck x to the power m plus k is equal to 0. So we first collect the x to the coefficient of x to the power m plus k. So it is m plus k taken common. If we take this two term, thus this becomes alpha square, because m plus k taken common. Once m plus k taken common, it is m plus k minus 1 plus 1, which is m plus k. So it is m plus k whole square, and from this we will have alpha square. And the other term is summation over k ck x to the power m plus k plus 2 is equal to 0. In this case, the lowest power of x to the in this expression is x to the power m, because for k is equal to 0, so we get the coefficient 0 is equal to m square minus alpha square is equal to 0. Since c is not equal to 0, m as c0 is not equal to 0. In this case, alpha can be anything. Say alpha is 1/3. Say alpha is 1/3. Then m1 is equal to 1/3 and m2 is equal to minus 1/3. So delta m is equal to 2/3, so which is not an integer, so we can get both the solutions. And when these roots differs by an integer, say alpha is equal to half, then m1 is equal to half, m2 is equal to minus half, and delta m is equal to 1, we will get one solution. We shall see all these things in connection with Bessel function. Now we come to the point, the theorem A2. The roots are repeated roots. The roots of the initial equation, we shall consider two differential equations which have repeated roots. Theorem examples on Theorem-II. The xy double prime plus y prime plus xy is equal to 0. It is x is equal to 0 is a removable singular point, so we write the solution as ck m plus k minus 1. When we multiply this is m plus k minus 1. From this second term we have ck m plus k x to the power m plus k minus 1, and for this term we will have ck x to the power m plus k plus 1. So we take the ck m plus k common, so this is m, again it is this, and the other term is here the lowest power is x to the power m minus 1, whose coefficient of c0 m square is equal to 0, which gives that m is equal to repeated roots 0 and 0. Here we can get only one solution by Frobenius method. And the second example we consider x into 1 minus x you see that q1 here is 1 minus 5x x into 1 minus x, and q2 is minus 4 x into 1 minus x. So they are, the singularity in q's are removed in x function. So we write, so that we take the solution solution y as ck summation over k ck x to the power m plus k, and if we differentiate it twice we get k ck m plus k minus 1 x to the power m plus k minus 2. Then for this term 1 minus 5x and for the last term minus 4 summation over ck. Now you see that if we multiply this x with this, the power will be x to the power m plus k minus 1, and when this is multiplied with this we will have the same power. When x, so summation over ck, the m plus k is common everywhere, so it is m plus k minus 1 from this term, and from this term it is plus 1. The coefficient is x to the power m plus k minus 1. So the x to the power m plus k minus 1 has two contributions. When this term is multiplied by this, the coefficient m plus k is taken common, so this and this term, and all the other three terms contributes to x to the power m plus k. So the minus sign, summation over ck, first there are few terms from the first term. This is from the first term. From the second term it is plus this term is negative, this term is negative, so this is plus. Let me simplify this term. This is m plus k whole square minus this term. If we collect this term, this is ck Now for initial equation we have x to the power m minus 1's coefficient with c0, m square is equal to 0. Again the roots are 0 and 0. Now we come to the example of Theorem-III. Theorem-III says that the roots differ by an integer. So we take some example where roots differ by an integer. We have already considered an example where alpha is equal to half, the roots differs by an integer. X is equal to 0 is a removable singular point, so we write the solution as with c0 not equal to 0 as usual. So whenever we plug this into the relation, we get this is form of this term. So this term gives or if we take all this term and this last term has the power m plus x to the power m plus k. If we couple this, it is m plus k whole square minus 1 x to the power m plus k plus ck x to the power m plus k plus 2 is equal to 0. So the lowest power is x to the power m, which gives you c0, m square minus 1 is equal to 0, that is m1 is equal to 1, m2 is equal to minus 1, so delta m is equal to 2, which is an integer. So it says that this will definitely give you a root. This may or may not give you a root. So this is the statement of Frobenius-Fuch's theorem. The larger root of the initial equation will definitely provide a solution. This, the lower one, may or may not as the second example and the last example of this law to consider Again, see, the x is equal to 0 is a removable singular point. So we write the solution as if we plug this into this equation, for second derivative it is the factor, for this is the y prime term, this is the y term. Or if we multiply the first term, the power is m2, x to the power m plus k minus 2, and when we multiply it is m plus k. Sorry, when we multiply it is x to the power m plus k minus 1, there is another such term. So we first collect the coefficient of x to the power m plus k minus 1. It has a contribution from here. The term is m plus k minus 1, this term, and here we will have 1. And all the other three terms have x to the power for x to the power m plus k. So this sign is with minus. This term, so this is minus, this term is plus 3m plus k, and this term is minus 1. Or ck m plus k whole square. I might have. Okay, this sign was wrong. The differential equation had a, so this sign is minus. Had this sign been minus, then this is a minus sign. This is also minus. Please note the change in. So this is m plus k, and this is m plus k minus 2, x to the power m plus k minus 1, and then we can take the lowest power of x to the power m minus 1 gives you c0, m into m minus 2 is equal to 0. This gives you m1 is equal to 0, m2 is equal to 2, as c0 is not equal to 0. So the roots differ by integer. It will definitely give you a root solution. This may or may not give you a solution. This is the statement of second theorem due to Frobenius and Fuchs. In the next class, we shall consider a few simple applications on Frobenius-Fuchs method.